Hey Chemistry, Mrs. KJ here, going over 8.03 Review Nuclear Forces. Review concepts presented in the lessons, forces within the nucleus, and radioactivity and half-life. The nucleus is composed of protons and neutrons, which are made of quarks. Quarks exert the strong nuclear force on one another, holding the nucleons, or in other words, the protons and neutrons, and the nucleus together. When a nucleus is unstable because it has too many protons or too few neutrons, it decays and gives off radiation as particles or energy. Different types of radioactivity have different energies and penetrating powers. Goals for this lesson: to demonstrate mastery of the previous two lessons. And you can go to the student guide to get the answer keys. Key concepts and forces within the nucleus. Nuclear chemistry involves changes in the composition of the nucleus. Okay, so up until now we've been doing chemical or physical changes. Physical changes meaning it's the same substance, you just changed the form, like you cut a piece of paper. Chemical changes are all the other changes that you see, so rust or baking a cake, okay? Nuclear changes are very rare in that you just have fission and fusion, okay? And we're going to talk about those two words later, but it has to do with the nucleus actually changing. So you're changing from one element into a different element. Protons plus 1 charge and neutrons 0 charge make up the nucleus. Protons and neutrons are made of fundamental particles called quarks. Up quarks are particles with a positive 2/3 charge. Down quarks are particles with a negative 1/3 charge. Protons are made of 2 up quarks and 1 down quark. So when you add it all together, 2/3 plus 2/3 plus a negative 1/3, that's how you get that positive 1 charge. Neutrons are made up of 1 up quark and 2 down quarks. So when you add that up, 2/3 minus a third equals 0. That's how you get the neutral charge. Quarks attract one another to hold protons and neutrons together via the strong nuclear force. Quarks from one proton attract quarks from another proton or neutron, remember together they're called nucleons, via the residual strong force. Nuclear chemistry has many applications. So the nucleus is composed of neutrons and protons, which are composed of quarks. Therefore, we call neutrons and protons nucleons. Key concepts in radioactivity and half-life. Radioactivity is caused by decay of the nucleus. It occurs when unstable nuclei lose protons or neutrons. Nuclei are unstable when the proton to neutron ratio gets too high. Unstable nuclei decay to stable ones by giving off radiation. Radiation is particles, energy, heat. There's 3 types. You can have alpha emission, which is the helium nucleus, or 2 protons and 2 neutrons. You can have beta emission, which is a high-speed electron or positron, which is a positive electron. It's weird, I know. The 3rd type is a gamma emission, which is electromagnetic waves. Radioactive emissions can change the composition of the nucleus. The time of radioactive decay is measured in half-lives. Heavy isotopes change to stable ones in a series of radioactive decays. Alright, so we're going to look at problem set 97 and 98. Oh, but before I do, there's always links at the end of the reviews, so if you want to look and check out some of these links, feel free to do that too. Forces within the nucleus. So the objectives describe the differences between chemical and nuclear reactions, identify the force that holds protons and neutrons together in a nucleus, identify the particles that make up protons and neutrons. Very strong forces hold particles in the nucleus together. Chemical reactions involve the breaking and forming of chemical bonds between atoms. Okay, now that happens when you gain, lose, or share what? Electrons. Okay. Now we're talking about the nucleus. Now we're talking about the protons and the neutrons reacting. So these chemical reactions occur mainly because of interactions between the electrons of the atoms. Therefore, electrostatic forces, that is, attractions and repulsions between charged particles, like positive, positive, repel, positive, negative, attract, those are the main forces involved in chemical reactions. In contrast, nuclear reactions involve changes in the nuclei of atoms. The main force controlling nuclear reactions is called the strong nuclear force. The strong nuclear force holds the protons and neutrons in an atom together. Strong nuclear forces are much stronger than electrostatic forces. However, they do not affect chemical reactions because they act only over very short distances. Okay, so it's super strong, but it only reacts in such a tiny distance that basically the electrons can even ignore it. The strong nuclear force also plays another important role in the structure of atoms. Protons and neutrons are themselves made up of smaller particles called quarks. The strong nuclear force holds quarks together to form the protons and neutrons. Remember nuclear forces. Electrostatic forces between protons in the nucleus cause them to repel one another. Okay, so protons are all positive, they want to repel. And that's because of the electrostatic force. So electrostatic, always think of positive and negative. Now the strong nuclear forces hold the protons in a nucleus together. The strong nuclear force is much stronger than the electrostatic force, but the strong nuclear force acts over a much smaller distance. The strong nuclear force also holds together the quarks that make up the protons and neutrons. So the strong force is crazy strong, and it holds the quarks together, it holds the nucleus together, but it's only strong over a short distance. Okay? Electrostatic forces are stronger over a larger distance, which is basically why the strong force overrules the electrostatic force in the nucleus, but it can basically be ignored once you get outside the nucleus into the electrons. Describe nuclear forces. Explain why the strong nuclear force must be stronger than the electrostatic force in order to hold atomic nuclei together. Go ahead and hit pause, think it over. Solution. The electrostatic force is responsible for the attraction and repulsion between charged particles, so plus and minus. Particles with like charges repel one another, and particles with opposite charges attract one another. Protons are positively charged. The strong nuclear force holds protons and neutrons together in the nucleus. Solve. Electrostatic forces between protons cause them to repel one another because they are all positively charged. The strong nuclear force must be strong enough to overcome those repulsions and force the protons to stay together in the nucleus. Describe the structure of the nucleus. Use the terms quarks, protons, neutrons, nucleus, strong nuclear force to fill in the concept map. So hit pause, see if you can do it. And then, of course, the nucleus is made up of protons and neutrons, which are made up of quarks, which are held together by the strong nuclear force. Tip: quarks are electrically charged. Unlike protons and electrons, their charges are not whole numbers. Up quarks are plus 2/3, down quarks are minus 1/3. Alright, so we want to do problems 1, 2, and 3. So problem 1, which of the following statements is true? A, electrostatic forces hold the nucleus together. B, strong nuclear forces hold quarks together. C, strong nuclear forces are involved in chemical reactions. D, electrostatic forces cause electrons to attract one another. So go ahead and hit pause. And the answer is B, strong nuclear forces hold quarks together. All right. Number 2, what is the difference between chemical reactions and nuclear reactions? Hit pause, think it over, and chemical reactions involve interactions between valence electrons and atom. Nuclear reactions involve the nuclei of atoms. So chemical is going to have to do with the electrons. Nuclear, we're messing around with the protons and neutrons. Arrange the following particles in order of size from smallest to largest. Go ahead and hit pause. And the answer is quarks make up neutrons, nuclei contain protons and neutrons, an atom's nucleus is only a tiny fraction of the atom's total volume or size. Therefore, the correct order is quark, neutron, nucleus, atom. All right, let's go ahead to the next part. And it says radioactivity and half-life. Objectives: describe the 3 most common types of radioactive decay, define half-life, perform half-life calculations. During radioactive decay, an atomic nucleus gives off particles, electromagnetic radiation, or both. As a result of radioactive decay, an element may change into a different element. Most elements have some isotopes that are unstable. Okay, so isotopes. Atoms of the same element but different numbers of neutrons. Okay? The nuclei of these radioactive isotopes can break down to form new elements. The breakdown of radioactive isotopes is called radioactive decay. The nuclei of a radioactive isotope decay at a specific constant rate. The amount of time required for 1/2 of a sample of radioactive isotope to decay is called the isotope's half-life. There are 3 main types of radioactive decay: alpha emission, beta emission, and gamma emission. During alpha emission, a nucleus gives off an alpha particle. An alpha particle is a helium nucleus, so 2 protons, 2 neutrons. During beta emission, a nucleus gives off a beta particle. A beta particle is an electron. During gamma emission, a nucleus gives off a photon of high-frequency electromagnetic radiation, so a gamma ray. And remember, other types of electromagnetic rays would be like microwaves, X-rays, radio waves. Okay, so this one is gamma. Alpha emissions and beta emissions both change the makeup of the nucleus. That is, they change the number of protons and neutrons in the nucleus. Gamma emission has no effect on the number of protons and neutrons in the nucleus. It often accompanies other radioactive processes and is the energy given off as the nucleus reorganizes itself after an alpha or beta emission. The table below gives some of the properties of these different types of radioactive decay. So alpha particle, the symbol is right there, so that's for the A alpha, or the helium, meaning the 4-2 with a +2 charge. They should have wrote +2 right here as well. The mass is 4 AMU, or atomic mass units, because there are 2 protons plus 2 neutrons, gives you a total of 4. Beta, there's our letter B, or an electron. The mass is very small, and the charge is -1. There's the abbreviation for gamma, and mass is 0, charge is 0. Remember, radioactivity. The 3 main types of radioactive decay are alpha, beta, and gamma emissions. Alpha radiation and beta radiation are made up of particles. Gamma radiation is made up of electromagnetic rays. The half-life of a radioactive isotope is the amount of time for 1/2 of the radioactive nuclei present to decay. The half-life is given isotope is constant. It cannot be changed by chemical reactions, time, or any other known process. So it's kind of cool. It's crazy that this happens, and yet it's very interesting that it happens at a constant rate. Compare radioactive decay processes. Which of these nuclear reactions gives off the most penetrating radiation? All right, so we have carbon changing into nitrogen with an electron. So which one is that? Is that alpha, beta, or gamma? That one would be beta. All right. Uranium changing into thorium plus helium. What type would that be? That would be alpha. We have Ra turning into Rn. And again, we have that helium. So that would be alpha. We have thorium turning into Ra plus helium plus gamma. So it has the alpha particle, but it also has the gamma. So that one is going to be the most penetrating. All right, and then consider the penetrating power of each radiation. Alpha particles can be blocked by a sheet of paper. Beta particles can pass through a sheet of paper, but can be blocked by a piece of aluminum foil or a few centimeters of wood. Gamma rays can pass through most substances. They can be blocked only by thick sheets of lead or concrete. All right, tip. A nuclear decay equation shows changes to atomic nuclei. A nucleus of an element is represented by that element's chemical symbol, along with its atomic number and its atomic mass number. For example, the symbol 42He represents helium-4, nucleus with an atomic number of 2 and a mass number of 4. All right, and we'll pick up the next example in the next video.